Hello everyone, welcome to PICO Developer channel. In this tutorial, we will explore how to synchronize PICO avatars in a multiplayer environment using Unity Netcode and PICO Platform Services. To make things easier, I prepared a sample project which you can download and open in Unity, so you don't have to code along. Instead, I will walk you through the key parts of the implementation. We will be focusing on the PICO Avatar SDK's APIs for synchronization, how to send avatar data over the network, and how to apply the received data to avatars. Let's get started. Okay, before we move on, I recommend checking out the first tutorial on the PICO Avatar SDK if you haven't already. For this tutorial, I started with the project from the previous video and built on top of it. Most of the project settings remain the same, and I will point out the changes I made as we go. Let's open the package manager and have a look at the changes I made in the packages. I've updated the PICO SDK packages, so this project uses the PICO Unity Integration SDK version 3.1.2 and Avatar SDK version 2.1.1. And I also added the PICO Live Preview package, though we won't be using it in this tutorial. The main addition here is the Unity Netcode for Game Objects package, which enables multiplayer support. Now let's take a quick look at the main components I've added to the project. These are a few manager classes that help organize and control specific features. First, we have the Startup Manager. This runs some simple setup logic, like triggering the PICO platform initialization steps when the app starts. Next one is Platform Manager, which includes three key components. The first is the Platform Service Manager, responsible for initializing the PICO Platform Services that we will rely on in this project. It also provides an interface for managing multiplayer rooms. The other two components handle room management and network connection logic separately, keeping things modular and easy to maintain, and these are required by the Platform Service Manager. Then we have the Network Manager. This is Netcode's default network manager, but with one important detail. We have configured it to use PICO Transport as the network transport. This allows the project to use PICO Network Service for sending data, with the PICO platform acting as a relay server. To make this work, a PICO-specific transport component is added and referenced here. And finally, the most important manager in this tutorial, the Avatar Multiplayer Manager. This is where we handle everything related to synchronizing avatars across the network. It manages both the local player avatar and the remote avatars, and it is where we will focus most of our attention moving forward. As you can see, this component has a few references assigned. First one is the main user avatar. Next, there is a reference to the parent object of the user avatar, which is the XR-rig. We will use this transform to reparent the user to a spawn point when the user joins a multiplayer room. And finally, there are references to the spawn points themselves. Since this setup includes just one local local avatar, and one remote avatar, I've added two spawn points only. I have added a simple tool called the log-util that prints logs from my scripts. It helps track the app state during runtime, both in the editor and on the headset. There is also a simple UI for room management. It lets you list available rooms, create a new one, or leave the current room. Okay, let's move on and take a look at the code. First, I will show you the small changes I made to the user avatar script from the previous tutorial. I updated the platform service initialization logic here to use the platform service manager instead. I also replaced the original debug log calls with my log utility. As I mentioned earlier, we have a couple of manager classes in the project. I won't go into too much detail on components other than the Avatar Multiplayer Manager, but to give you a better idea of how everything connects and works together, I will quickly walk through their implementation now. So I'm starting with the Startup Manager here. As you can see, this is a singleton class. In its start method, we'll launch a coroutine that calls the Platform Service Manager to kick off the PICO platform initialization steps. This section here handles a simple timeout check, just in case initialization takes longer than expected or something goes wrong. Other than that, there is not much else going on in this class. And next up is the Platform Service Manager. This is also a singleton class, and it holds references to the platform controllers for both room and network management. It exposes a property called rooms, which gives us access to the room controllers methods, like joining, creating, or leaving a room. The init platform services method, which is called by the startup manager, begins by initializing the core service to enable PICO platform features. If that goes smoothly with no errors, we then fetch the logged in user's information using the user service and assign it to a class level variable. You see, we are simply calling get logged in user method here and assign it here. As the final step in this setup, we also initialize the PICO game service, which is required for matchmaking and room services. In this method, we first ensure that the game service is uninitialized, just as a best practice. Then we go ahead and initialize it. If everything is successful, we move on to initialize the controllers registered to this class. Each controller, the controllers are room and network controllers. So each controller implements a method called delay init, which is where their own setup happens. Everything we need is now initialized. Since we have covered the key functionalities of the Platform Service Manager, we can move on to the next ones. Of course, feel free to dig into the code and explore the full implementation in your own time. Now there is one more important step to get room, network, and matchmaking services working. You will need to log in to the PICO Developer Console with your PICO account. Then select your app and navigate to the Matchmaking tab under Platform Service. Before you can use these services, make sure to click on this button to activate them. You will see this pop-up warning you that it might take up to 10 minutes for the service to become available. And once this service is active, you can start using room, network, and matchmaking services. All right, let's take a look at the Avatar Multiplayer Manager. As you can see, this game object has a network object component attached, and that's because this class is a network behavior, and Unity automatically adds a network object when you use a network behavior. Now the reason Avatar Multiplier extends network behavior is because it uses both server and client RPC methods. We send avatar data from client to the server using this ServerRPC, and then the server sends avatar data back to the other clients using a ClientRPC. I will go into more detail on that shortly. So first, let's scroll up and take a quick look at the class itself. As mentioned, it's a network behavior, and we have a few references here. User avatar, avatar's parent, and the spawn points. We are keeping track of two avatars, the local user avatar and one remote avatar. Since this is a sample limited to 2 players, that's enough, but if we were supporting more players, we would likely use a dictionary to manage them dynamically. In the awake methods, we do a simple check to make sure the spawn points are assigned. Then in the start method, we confirm that the user avatar is assigned as well. We also register 2 event listeners, one for handling player-related events and the other for room-related events. So room-related events are triggered by actions involving the logged-in user, the main user, like joining a room, leaving it, or being kicked out. On the other end, player-related events are tied to the other users entering or leaving the room. I will come back to the update method a bit later. First, let's take a look at these 3 methods right here. So when I want to send the user's data over the network, I need to make sure the avatar is fully initialized and ready. To do that, I register a listener for the onUserAvatarReady event in this onEnable method and remove it in onDisable. In the callback, here I simply assign the avatar to the main user avatar variable, which is defined at the class level. Okay, let's continue with how we handle room-related events. When a player joins, leaves, or gets kicked out of the room, those events are handled in this callback method. In this callback, if we receive the processing status, that means that the player status in the room isn't finalized yet, so we simply return early in that case. Next, if the event type is a room status event and the status is in room, that means the player has successfully joined the room. At this point, we are connected and Netcode has started. So we move the player to their multiplayer spawn point by reparenting their XR rig to one of the predefined spawn points. If we take a quick look at the getSpawnPoint method, you will see it returns the first spawn point for the room owner and the second one for the other player. Right after we reparent the player, we make sure that its local position and rotation are reset. Now that we are officially in a multiplayer room, we can start sending the user's avatar data. In the Start Sending User Avatar method, we reset a counter that helps control how frequently packets are sent, and we set a flag that the update method uses to start or stop sending avatar data. There is also a Stop Sending Avatar method, which simply disables that flag to stop sending data when needed. Okay, now that we have handled the local player's avatar setup, we also need to check if there are other players already in the room, and if so, we will want to create and set up their remote avatars as well. Here I check if there are any other players in the room. If so, I retrieve the current room data and loop through all the players, skipping over our own. Since we are working with a 2-player setup, we expect just one other player. Before creating their avatar, we check if a remote avatar already exists, and if it does, we destroy it. Then we load the remote avatar by passing the player's user ID and assigning a spawn point as its parent. Okay, let's take a look at how we load a remote avatar. This method should look familiar if you watched the previous tutorial. Loading a remote avatar is very similar to how we load the main user avatar. Let me bring up the script we used for user avatar so we can compare the two. As you can see, both methods start by setting the avatar capabilities. The manifestation type is the same. We are still using full body avatars. One of the key differences is in the control source type, which is set to other player here, since this avatar will be controlled by another user. And for input source type, we use remote package because the avatar will be updated using the data received over the network, rather than the local headset and controller input like we do with the main user avatar. The record body level defines how much avatar data we want to send over the network. You can reduce the data size by choosing options like basic bone or device input, but for more precise results and to avoid recalculating inverse kinematics on the client side, full bone is preferred. That's also the default setting on PICO Avatar app, so the main user avatar uses full bone even though it's not explicitly set. The rest of the method is pretty straightforward. We pass in the user ID and the capabilities to load the avatar, and then set its parent to the spawn point. Alright, let's scroll back up to where we left off. We already covered what happens when the player joins a room. Now let's take a look at the case where the player leaves the room. In this situation, we simply stop sending avatar data and destroy the remote avatar, since we are no longer in a multiplayer session. Okay, let's also have a quick look at how we handle events related to other players. In the callback method, if the event is triggered for a joining player, we get their player ID and the spawn point transform, then we call the load remote avatar method. If the event is for a player leaving, then we simply destroy the remote avatar. Okay, let's shift our focus to how we send and receive avatar data. We will start by revisiting the update method. This method performs 2 important tasks every frame to keep avatar synchronization smooth and consistent. The main goal is to reconstruct what other players are doing using the data we have received from them. First, we calculate network sync time, which represents the point in time we want to simulate. By subtracting a small playback interval, we intentionally introduce a slight delay. This helps reduce jitter caused by network latency. You can actually tweak the playback interval from the PICO Avatar app we have in the scene. Next, we call SyncNet simulation. This tells the PICO Avatar system to simulate the remote avatars based on the buffered data we have received so far. It may not be perfectly real-time, but it creates much smoother and more stable motion. Here in the update method, we also check whether we should send avatar data in the current frame and make sure that the main user avatar instance is assigned before doing so. Now let's take a look at what's happening inside the send avatar method. Inside the send avatar method, we first check whether enough time has passed since the last packet was sent. We don't want to send data every frame. And just like the playback interval, the record interval can be adjusted through the PICO Avatar app we have in the scene. Next, we get the avatar entity and ask it to record a packet using the current network sync time. We also update the last packet sent at timestamp. Then we create a memory view which contains binary data from the avatar. And if the memory view is valid, we call our ServerRPC method and pass in the byte array from the memory view. Okay, let's take a look at how the ServerRPC works. This method is marked with require ownership set to false, which means any client can use it to send their main avatar data to the server, even if they don't own the object. Once the server receives the avatar data, we want to broadcast it to all clients except the one who sent it. To do that, we loop through the list of connected clients and build an array of client IDs to send the data to. We then include this array in the ClientRPC send params. I also grabbed the sender's PICO user ID from the Platform Service Manager, so the receiving clients know which avatar the data belongs to. In this two-player example, it's not necessary, but if you were to scale up to more players, this would be important for identifying which avatar to update. Finally, we call the ClientRPC, passing along the avatar data, the user ID, and the list of clients we want to send it to. Now let's take a look at the ClientRPC method. Since we are only dealing with one remote player in this setup, we can directly update the remote avatar using the incoming avatar data. But before doing that, we make sure the remote avatar exists and it is ready to use. We start by creating a memory view from the received byte array, then call apply packet on the avatar's entity to apply the data. And since memory view is a native object, we call check delete here to mark it as OK to release its allocated memory afterwards. Alright, we have now covered all the key parts of the implementation, so it's time to do some testing. I will be using my PICO headset alongside the Unity editor to test multiplayer. Before we jump in, let me quickly show you a few configuration steps I made to make testing smoother. First, I'm using Unity's XR simulator. You can enable it in player settings. Just make sure it is set to run only in the editor mode. Also, in the previous tutorial, I had swapped out the tracked pose driver on the main camera for the non-input system version, but since XR Simulator relies on the input system, I have reverted that change. Also, we still need to adjust the input settings to make sure the app continues receiving input when system overlay appears. To do that, go to the input system package settings and set background behavior to ignore focus. Alright, we are all set and let's go ahead and build the project. Alright, let's start by running the project in the Unity editor. One important thing to keep in mind, if you have set up PC debug settings using your PICO account access token, you won't be able to test multiplayer with that same account logged into your headset. So make sure to create a second account and use it either for the editor or for the headset. As you can see, the XR device simulator is already active in the scene. While it doesn't exactly replicate the experience on the headset, it does allow us to move around and interact with the UI. Looking at the logs, everything seems fine so far, which is a good sign. Okay, let's go ahead and create a room. Alright, we have successfully created and joined a room. Now let me join to this room from the headset as well. Okay, great. The headset player has now joined the room and the avatars are loading in. Since the headset player isn't the room owner, it's spawned on the opposite side, just as expected. And everything is looking good so far. As I also demonstrated in the previous tutorial, we can move the avatar around in the editor using the editor input device. Let's try that now and see if the movement synchronizes properly with the headset. First, let's enable the editor input device game object. Make sure the user ID field matches the actual avatar's user ID. Okay, both players are connected, so now we can move the avatar around by adjusting the assigned transforms in the editor. And yeah, this works just as expected. Okay, that wraps up our tutorial on synchronizing PICO avatars. I hope this helped you get a clearer picture of how everything works together. Thanks for watching and see you in the next one.